Okay, we're going to continue on here talking about chapter 15, I believe it is. So in chapter 15 here, we started talking about KSP. KSP is the solubility product. It is an equilibrium constant really for things that are pretty much insoluble. So kind of an equilibrium constant for insoluble salts. And that means we do get sort of a different sort of setup a lot of times with the KSP sort of reaction. We typically will always have solids on the left-hand side or reactant side of the equation, and then we would have aqueous ions, positive and negative aqueous ions on the product side. So typically when we do write the KSP expression, it typically is really just the products, as that's typically how we should kind of set up our KSP expression. So for example, I think we finished last time, we looked at like silver chloride, which is normally insoluble. When it does break apart, we will get a silver ion and a chloride ion. And once again, we would write our KSP here would be the concentration of silver times the concentration of chloride. Now, even though, again, based on solubility rules, it does say that obviously silver chloride is insoluble. Even things, as we talked about last time, that are technically insoluble based off of those rules, there is some degree of solubility that will happen. So even if this is a very, very small amount, it will break apart into some ions here. We work KSP problems kind of very similar to how we work normal sort of equilibrium problems. We do typically use sort of a different letter sometimes to represent the change, and that is S. So if we were looking to figure out the KSP of this guy or the solubility of this guy, we would start with zeros. The change part here would be plus S, and at equilibrium, it would be S and S. Here, S is the molar solubility, and the molar solubility is the molarity, basically, moles per liter. So that is one common sort of solubility that we solve for. And typically when you do solve for the S here, that would be also, in most cases, the solubility of the insoluble salt there. We also look at solubility a lot of times in grams per liter. And again, remember that the one that sort of ties both of those together is the molar mass. So we can use the molar mass to go from moles per liter to grams per liter in this particular case. If we were interested in how many grams per liter, we would dissolve it in. Remember as well, we still use coefficients. So if you do break apart into, say, a couple of positive ions, then you should put 2s. You also would need to square the KSP part of that as well. So again, works really the same way. In a problem where we're looking for the solubility, either molar solubility or solubility in grams per liter, you definitely should do an ice table, and that's a good way of doing it. If you are really just looking for the value of the KSP, which is another sort of way that we do it, a lot of times you will be given the solubility of a substance. You could either put it into the ice table, and when you would, whatever they gave you in terms of the molar solubility would be what S would equal in the table, and you can basically just solve it that way. Or if you, again, understand how concentrations work in terms of the whole thing to the ions, you could just plug it right into the KSP expression and also get the KSP value that way. So definitely in this type of problem, you would need to use an ice table. And the other problem where you're solving for the KSP, you might not necessarily need to use an ice table again, but it can help you understand certain parts of the calculation. Again, it's a very common error that people make, which is, again, I times it by 2. Do I still need to square it? So sometimes people talk themselves out of maybe doing the right thing. So maybe with the ice table, even in both situations, it will kind of walk you through what you need to do. Any questions on any of that stuff there we talked about last time? All right, so I believe we did the silver chloride example at the end, if I'm not mistaken. So I think we're here. So why don't you give this a go? Calculate the concentration of aluminum. Dramatic pause, +3. I'm not sure why my +3 went way over there. In a saturated solution of aluminum hydroxide. Not sure why my 3 is over there either. There we go. All right, here's the KSP value at 25 degrees. So give that a go. We're looking for the aluminum concentration here. Take a few minutes, see what you come up with. Okay, let's take a look at this. So we're looking for the concentration of aluminum in a saturated solution of aluminum hydroxide. So we have a KSP, so automatically we should know we can do our aluminum hydroxide. Going to break apart again into its ions, which would be the aluminum ion plus 3 hydroxides. If we were going to write our KSP expression here would be the concentration of aluminum times the concentration of hydroxide, and we do need to cube it because of the 3 that is there. So doing our ice table here, we're going to start with 0 here of each of these guys. Change is going to be plus S, and again, we want to make sure that we also take the coefficient into account here. So that's going to be plus 3S. That will give us, I blank screen, there we go. That will give us S and 3S in this case. Any questions on the ice table here? So like normal here, we're just going to put this into our KSP expression. That means that we would have S times 3S. Once again, we do want to make sure we are still cubing it like we should. And that will equal 2 times 10 to the minus 32. Bless you. At this point, we're going to clean up maybe the left-hand side. Why not? That is a 27, S to the 4th. My experience, a lot of people forget to actually cube that number. So make sure that you actually cube the number there. 3 times 3 times 3. Not just, obviously, the S's here. Going to equal 2 times 10 to the minus 32. We're going to divide that 27 to the other side. And if we do that, 2 to the minus 32 divided by 27, and a little extra negative there, going to give us like 7.407 times 10 to the minus 34. We now want to take the 4th root there. So we're going to take that to the 4th root, which is 1 divided by 4. And if you do that, so basically here to the 4th root, and that will give us an S of about 5.2 times 10 to the minus 9. If you don't have your calculator in scientific notation, you probably got a lot of zeros and like a 5 at the end of it because I ran out of room and your calculator. By the way, on your calculator, if you're not sure, take the 4th root in case you don't have a button. You can take the number, right? Put parentheses, do a caret or whatever you like to do, 1 divided by 4. Yeah, so if you want to do that on your calculator there, that's how you do the 4th root. Or if you have sort of a root button, you obviously can use that as well. If you want to do the square root, 1 divided by 2, you want to do the cubed root, 1 divided by 3. So that's, again, a way you can punch it into your calculator. So something like this number to the 1 divided by 4 would basically do that root for it. Any questions on that there? So that S is our molar solubility. And in this particular case, we are looking for the concentration there of aluminum. And we can see from our table that the concentration of aluminum does equal S, which means the aluminum ions concentration would be something like 5.2 times 10 to the minus 9, I think is what I had. That would be some molarity there. Although it didn't ask it, the concentration of a hydroxide in this case would be 3S. Yeah, so we would take 3 times 5.2 times 10 to the minus 9. Times it by 3 would be good. We get something like 1.6 times 10 to the minus 8 molar. Again, it didn't ask for it, but if we needed to, we could get the hydroxide concentration. The molar solubility of aluminum hydroxide would also be the value of S. Yes, again, if you look at aluminum, it's a 1-to-1 relationship. If you look at hydroxide, it's a 1-to-3 relationship, which means if you divide that number by 3, you get back the original number. So again, that S is basically the molar solubility of the whole thing. Question on any part of that calculation there? Let me double check here. So we took 2 to the minus 32 divided by 27. And then we took the fourth root of that, basically, which gives us 5.2 times 10 to the minus 9. So again, in your calculator, you could take the number, probably hit the caret button, put a parentheses 1 divided by 4 and hit equals. And that's a way that you could do it now. Other questions? All right, so this is a table of some of the KSP expressions that you get, and obviously it does change based on the coefficients that we got there. So can we use KSP values to help us understand what salt would be perhaps more soluble than another? And we can in certain situations. So if you have salts that you're comparing and you're trying to figure out which one would be more soluble than another salt, you can directly use the KSP values only if all the salts break apart into the same number of ions. So if all the salts break apart into the same number of ions, you could directly use the KSP value that you would find in the table, and you can make a good prediction as to which one would be more soluble. So what I mean by that is if we look at silver iodide, when it breaks apart, it is a silver ion and an iodide ion. When we look at copper 1 iodide, when it breaks apart, we get a copper 1 ion and an iodide ion. And if we look at calcium sulfate, when it breaks apart, we get a calcium ion and a sulfate ion. So the grand total of ions on all three of these guys is basically 2. So because they do break apart into the same number of ions, you can look at the KSP values in the table and use them to make a prediction in terms of solubility. The larger the KSP value in that comparison, the more soluble something would be. And that is because if I have a large KSP value, I should mainly have reactants or products. Large K value means you have more products at equilibrium. And in this case, all the products are always the aqueous ions, which means they're soluble. So if you have the large KSP value in the group, you can compare it. So if you were to look up the value, you would see that calcium sulfate has the largest KSP value, which would be more soluble. And silver iodide in this case would have the smaller of all three of those guys and be least soluble. So by looking at KSP, you could get an idea of, if you have some ions in solution, which one you would expect to precipitate out first. Again, you could do a direct comparison if everybody breaks apart into the same number of ions. Now, if they do not break apart into the same number of ions and you want to kind of compare which one would be more soluble, you cannot directly use the KSP values to do that. You actually have to do the calculation like we just did in those previous problems and calculate the solubility of each of those salts and then compare it. So to illustrate that, if we look at a few different salts here and we look at the KSP values, we have copper 2 sulfide, which breaks apart into a copper 2 and a sulfide. So that is 2 ions. We got silver sulfide, which breaks apart into a couple of silvers and a sulfide ion. That would be 3 ions. And lastly here we have our Bi2S3. which would break apart into a couple of bismuths and a few sulfurs there. It's like 5 ions. So in this case, they do not all break apart into the same number of ions. If we looked at the KSP values from the chart, we would see that it is actually this guy here that has the largest KSP value. And this guy here has the smallest. So if you went by solely the KSP values in the table and comparing these three salts, you would incorrectly say that this guy here is the most soluble and this guy is actually the least soluble. When you actually do the calculation like the ice table and stuff that we did earlier for each of these guys, what you actually see is in terms of molar solubility, it is the copper 2 sulfide that's actually the least soluble, and it's actually the Bi2S3 that is the most soluble. So in a situation like this, you should not use the KSP value to compare. You got to just kind of do the calculation for each of them and compare them after that. But if you had a situation like we had previous slide, everybody's the same number of ions, you can absolutely just directly use the KSP values to help you make that determination. Questions on that there? Okay. So let's talk a little bit about the common ion effect and the effect on solubility. So the presence of a common ion will decrease the solubility of a salt. And the reason for that is, as we've been talking about, pretty much in all of these equilibriums, solid on the left, aqueous ions on the right, which means if you have a common ion that is there, you have one of these guys there, and that means the Chatelier's principle would tell you is going to shift away from the side it was added to, and that is going to push it back to being more insoluble. So kind of like what we saw with the common ion in sort of buffers situations, it will push the equilibrium back to keeping everybody together. In this case, it will push the equilibrium back to the left there, keeping everybody together as a solid and making it more insoluble in this case. So as comparison here, if we look at the molar solubility of silver bromide in pure water versus what it is in 0.001 molar sodium bromide, this is the KSP for silver bromide here. So if we did our silver bromide in pure water, we would set up our ice table. We would end up with, again, a silver ion here plus a bromide ion. Initially, we would have 0 and 0. Change would be plus S and plus S, which means at equilibrium, we would have S and S. That means going into our KSP expression of the silver ion times the bromide ion equals our 7.7 times 10 to the minus 13. Basically, that gives us S squared equals 7.7 times 10 to the minus 13. Taking the square root there of both sides will get us something, 7.7 to the minus 13. Looks like it will give us a S value of 8.8 times 10 to the minus 7 molar. That would be the molar solubility of silver bromide just in water. That's pretty much the same type of ice table that we did on our previous problems here. Any questions on that one there? So now let's see what happens when we have silver bromide and we actually put it in a solution that also contains sodium bromide. So if we look at our silver bromide like we had on the other side, again, giving us our silver ion and our bromide ion. In the case of the second solution, we have sodium bromide. And sodium bromide will break apart into sodium ion and a bromide ion. That is because sodium is soluble in everything, which means it will be a solution, right? And it will be a strong electrolyte and will break apart. The common ion in this case is obviously the bromide. So that is our common ion in this case. So when we do our ice table with the presence of that common ion, it is slightly different than what we do when it's with water and no common ion is there. Initially here, we would have 0, but once again here, kind of like when you do buffers, this will not be 0. We will have an initial amount of that. And that initial amount is going to come from our sodium bromide solution. So if the entire concentration is 0.001, the sodium ion or the bromide ion there would be 0.001. So we will have that initial amount again coming to here. It is a 1-to-1 relationship between these guys, which means this concentration and this concentration will be the same in this case. The rest of the table here is going to be very similar, plus S and plus S. This means when we reach equilibrium, we will have S and 0.0010. Remember that this actually is plus S, not minus S on that side. Any questions on that ice table? So kind of similar to if you again did sort of an ice table in a buffer situation, you actually are starting with a concentration there of an ion on that side. We'll put this into our KSP expression, which in this case will give us S times 0.0010 plus S equals our KSP value, same KSP value, 7.7 times 10 to the minus 13. KSP values are typically small values, which means when they reach equilibrium, you mainly have reactants or products. So small value K means you mainly have reactants, yeah? So it is still a K value, it's still a small K value, which means you could still do an assumption like we did in a regular sort of ice table. So we could assume here that S is equal to 0. Just like when we do our X's are equal to 0, we do not get rid of them all. It is the same deal. It's really the X's we're going to, in this case, most likely add or subtract, but in most cases we'll be adding in this case. So that will reduce down, our guy here to, I'll go up here in the top left corner. That will give us S times 0.0010 equals 7.7 times 10 to the minus 13. That looks a little bit more manageable. We're basically just going to be dividing in this case. My calculator turned on, maybe we'll divide. 7.7 to the minus 13 divided by 0.001. Gonna give us an S value here of 7.7 times 10 to the minus 10. You should check it like normal, so we could divide by 0.001, times it by 100, but I would say in most of these cases, you probably will be good to go on all of them. So it's not even 0.1%, so it's very, very small. So that means that the molar solubility of our compound here with the presence of the common ion is 7.7 times 10 to the minus 10. Where is it more soluble in this case? Yeah, it is more soluble in water. That is times 10 to the minus 7, which is a larger number than times 10 to the minus 10. So without the common ion there, it's not going to have the equilibrium pushing back to the solid. With the common ion there, it is pushing back to the solid. That would obviously decrease the solubility of that. Any questions? So again, that presence of the common ion in most cases will decrease the solubility of it. All right, so why don't you give it a go here? I think we got one. Perfect. The KSP of silver chromate is 9 times 10 to the minus 12. What would be the solubility? We'll do the molar solubility here is good. We'll do the molar solubility. of this compound in a solution that already has 0.1 molar potassium chromate. We'll take a few minutes there, see what you come up with. Okay, let's take a look. So we have the KSP as silver chromate. So we know that really is the thing that's going to set up the equilibrium. So we'll start with our silver chromate here. We're going to break it apart. In this case, we will get 2 silvers and a chromate here. That would give us a KSP expression that looks like silver. And once again, here we would need to square it because of the 2 times the chromate here, which does not need anything because the coefficient there is 1. And that obviously would equal our 9 times 10 to the minus 12 in this case. The potassium chromate is going to break apart because it's a salt and a strong electrolyte. And again, potassium is soluble in everything. That's going to be a K2CrO4. We'll break apart into a couple potassiums and a chromate here. Once again, it is the chromate that is the common ion in this case. In this case, it is a 1-to-1 relationship between the chromate and the potassium chromate, which means our initial concentration for the chromate here will be the 0.1 molar here. This guy would be 0. Any questions on that there? Change part going to be plus, again, 2s because of the coefficient, and plus s in this case, going to give us an equilibrium here of 2s and 0.10 plus s. Any questions on the ice table where any of the numbers came from, right? Okay, so then what we're going to do, like normal, we're going to put this into our expression. So putting this into our KSP expression will give us 2s, and once again, we do need to square it, times 0.1 plus s is going to equal 9.0 times 10 to the minus 12. Well, once again, that does look pretty small, so I'm going to assume s is equal to 0. So again, that's going to get rid of the s that we got going on right there. That would then get us really like 4s squared, remembering to also square the number there, times 0.1 equals 9.0 times 10 to the minus 12. I'm going to multiply these guys together and then divide it over to the other side. So I'm going to multiply that and then divide. And that is going to give me here 4 times 0.1. And then we're going to take 9 to the minus 12 and divide it by that. And it looks like we will end up with s squared equals 2.25 times 10 to the minus 11. Obviously, we're going to do a little square root there on both sides. And if we do that, we get like a 4.7 times 10 to the minus 6. And again, that would be molarity here. Basically moles per liter solution of our silver chromate. If we wanted how many grams per liter, we would get the molar mass there of silver chromate and do the conversion, right? And we can end up with grams per liter. We should also check it, but once again, if you do check it, we would check it by taking our S value there, dividing it by 0.1, times it by 100. And obviously, you're like at 0.004%, so you're perfectly good, like in most cases with this. Question on that calculation there. Okay, so the presence of a common ion obviously will have an effect on the solubility of a salt. In this case, it will actually decrease the solubility of a salt. So there are several factors that can affect the solubility of salts. One of them is what we just talked about there, common ion. Another factor that can affect the solubility of a salt is actually pH. And pH and solubility The presence of a common ion, as we saw, decrease the solubility. When we have insoluble bases, they typically will dissolve in acidic solutions. And if we have insoluble acids, they will dissolve in basic solutions. So the pH is an important sort of factor as to whether or not you might see something precipitate or not. So for example, if we look at magnesium hydroxide here, and we got the KSP there of 1.2 times 10 to the minus 11. Get rid of that, I think. All right, so if we were just to run through our solubility table here and figure out the molar solubility, again, initially here, this would be 0, this would be 0. Change would be plus S plus 2S, once again, because of the 2. That means at equilibrium, we would have S and 2S. If we wrote our KSP expression, it would be the concentration of magnesium times the concentration of hydroxide. Once again, we do need to square it as well because of the 2 that is there. And that would equal 1.2 times 10 to the minus 11, I hope is what I had on that. So at this point, we'll put our S's in. This will give us S times 2S squared equals 1.2 times 10 to the minus 11. Combining everything on the left-hand side, and again, remembering to also square the number, will give us a little 4S cubed is equal to 1.2 times 10 to the minus 11. Dividing the 4 to the other side and also taking the cube root of it, 1.2 to the minus 11 divided by 4. Let's do it step by step. That gives us 3 times 10 to the minus 12, taking the cube root. Do it like that, I think. 1 divided by 3. Going to give us a solubility of 1.44 times 10 to the minus 4. First off, any questions on that? That's pretty much very similar to what we've been doing. Okay, so how is this helpful in terms of pH? This is helpful in terms of pH because if we look at our ice table here, we have hydroxide, right? So the concentration of hydroxide in this case would equal 2 times S, which would be 2 times 1.44 times 10 to the minus 4. And that would give me 2 times 1.44 to the minus 4. A OH minus concentration of 2.88 times 10 to the minus 4. That would allow me to calculate the POH, which would be minus the log of 2.88 times 10 to the minus 4. We do the little log action there. Going to give us a POH of 3.54. Subtracting 14 will give me the actual pH of the solution at this point. And if I do that, the pH of this solution is approximately 10.46. So as we can see here, in a case where you might have a insoluble base or an insoluble acid, you could actually use the KSP value to figure out the pH of that particular solution. So here we would expect it to be 10.46, which does make sense since it has hydroxide, it is a base, so that is a basic pH. So why knowing that information about where sort of the baseline here of the solution is in terms of its pH is important. Let's say, for example, I decided to increase the pH above 10.46. What would happen to the solubility in this case if I brought the pH above 10.46? In order to increase the pH, right? The H plus concentration goes up or down? the H plus concentration would actually go down, right? Yeah. So it would go down as the pH goes up, which means if I brought it up like that, the H plus concentration goes down, but because the OH minus concentration is tied to that, the OH minus concentration would then go up. Yeah. And when you would raise the pH above 10.46 in this case, you would actually be adding more hydroxide to the system, right? And based on Le Chatelier's principle, if I added more hydroxide to the system, what's going to happen to the solubility? Is it going to increase or decrease? Well, hydroxide is on which side of the arrow there? Hydroxide is on the right-hand side of the arrow. So if I added more things on the right-hand side of the arrow, it's going to shift to the left away, which means we're going to actually get more solid in this case, right? So we would actually see the solubility of this decrease. So knowing that this solution is 10.46, and if you decided to add more base to it, basically bringing the pH above 10.46, and you had like a test tube there, you would expect to see more solid basically start to form because you're basically decreasing the solubility of those ions in that solution by adding more hydroxide. Question on that? Now, let's say I decided to lower the pH less than 10.46. In order to lower the pH, the H plus concentration in this case must go, it will go up in this case, right? The hydroxide concentration will go down. Looking at this equilibrium, if I increase the H plus, what will happen in this case? So I'm basically like increasing that H plus concentration, or if you want to look at it, removing OH minus. So H plus and OH minus, what do they make? H plus OH minus makes H2O. That is essentially like removing hydroxide from that situation, right? And that's going to cause the equilibrium to shift to the right in this case, right? And when it shifts to the right, that's actually going to shift us to ions, which are aqueous and would increase the solubility. So by lowering the pH, and you don't even have to make it acidic, you just need to get it lower than 10.46, and you'll start to actually see it start to increase the solubility. So you don't necessarily have to drop it way into acidic. If you do, it definitely will make it much more soluble. But just lowering it below 10.46, which is still basic in some cases, you'll start to see more of the solid start to dissolve because of that shift in the equilibrium. So if we increase the pH above 10.46, it decreases the solubility. If we lower it below 10.46 in this case, it actually will increase the solubility. So pH plays a really important role in terms of solubility. And that's why in some of those qualitative analysis experiments that we'll be picking back up, I think, after spring break, a lot of steps have you, add some acid, then add some base and check the pH, make sure it's acidic or make sure it's basic. So by adding and changing the pH, it allows certain substances to be more soluble and other substances to be less soluble, which is obviously of advantage when you're doing something like qualitative analysis. Any questions on pH here and how it affects it? So in order to really understand, how the solution will sort of affect, you might need to calculate the actual pH of that solution and then kind of judge what you're doing in terms of the pH. But just generically speaking, you can look at it and understand, obviously, if you increase the pH, you're adding more OH minus, which should decrease the solubility. Or if you lower the pH in this case, or this example, you would be making water and removing OH minus. So these are two factors, as we just saw there, that will affect solubility. Common ion can play a role, and obviously pH of the solution can also play a role. That is why in the two sentences on the previous slide, it said that insoluble bases are soluble in acidic solutions, again, that's going to increase the solubility, and vice versa there. Insoluble bases or insoluble acids will be soluble in basic solutions. So will we get a precipitate form? We talked about at the very beginning here. We can use Q to help us decide that. Once again, Q is a reaction quotient. It's calculated the same way as K and KSP. So Q is still calculated the same as KSP in this case. This will tell us again if we would expect to precipitate the form or not. If we calculate Q and it's greater than the KSP, we would expect a precipitation to occur, because basically it would have to shift to the reactant side to kind of reach equilibrium. If Q is less than the KSP, it would shift to the right-hand side, and those are all ions, so it would increase the solubility of that, and no precipitation will occur. So let's see if we can figure this out here. If we took 2 milliliters of a 0.2 molar sodium hydroxide solution and added it to 1 liter of a 0.1 molar calcium chloride solution, would we expect a precipitate to form? So in order to make that judgment, a couple of things you might want to think about, obviously, are the ions that are floating around, right? Basically, these are two solutions. So when they do go for a swim, yeah, basically you got some sodium ions floating around, you got some calcium ions, got some hydroxide ions, and you got some chloride ions. So if you think about solubility rules, is there a combination at all in there that would make a solid? And that would be the combination that could make a solid. Again, the sodium is soluble in everything, right? Chloride soluble in everything except for silver, lead, and mercury 1, which is not in the mix here. So those guys are just going to float around. So is Q greater than the KSP here? The KSP is 8.0 times 10 to the minus 6 for calcium hydroxide, which is our only option. So I'll let you do it. Why don't you calculate Q here and see if we would expect a precipitate to form based on these conditions. Okay, let's take a look here. So again, our possible guy is our calcium hydroxide, which once again would break apart into a calcium ion and a couple of hydroxide ions. So our KSP would look like that. Our Q would also look like that. So it would be the calcium concentration times the hydroxide concentration. Again, we would square it. The key here is we pretty much want the concentration of each of those ions when they're mixed together. So we do need to actually figure out the concentration of, say, the hydroxide. And the concentration of the hydroxide, the only source of hydroxide is sodium hydroxide, so it would come from there. This is a little M1V1 equals M2V2 action going on. So this would be M1V1 equals M2V2. Solving for M2 would be M1V1 divided by V2. So our M1 is for the sodium hydroxide 0.2 molar. Our V1 is 2 milliliters. And just to make sure I'm on the same units here of volume, I'm going to convert my 1 liter into 1,000 milliliters. So everything cancels out correctly here. And if I do that, you alternatively obviously can convert everybody to liters if you wanted to do it that way. 0.2 times 2 divided by, that would be incorrect because the total volume here would be 1,002 in this case. Total volume is 2 milliliters for the sodium hydroxide and 1,000 milliliters for our calcium chloride, which actually gives us 1,002 milliliters. So that is where the 1,002 comes from. All right, so putting in the right number there would give us 1,002. Going to give us a concentration of hydroxide of basically 3.99 times 10 to the minus 4 molar. That would be the concentration of hydroxide in the mixture together. The source of calcium is going to come from calcium chloride. So we pretty much need to do the same calculation to get the proper concentration of calcium. Calcium would then be the concentration of calcium, in this case, 0.1 molar. We're going to use 1,000 milliliters of it. And once again, our total volume when everybody's mixed together, 1,002 milliliters. That will give us a concentration for calcium of 0.1 times 1,000 divided by 1,002. Going to give us a 9.98 times 10 to the minus 2 molar. I can relate the concentration of sodium hydroxide to the hydroxide because when sodium hydroxide breaks apart, you get a sodium ion and a hydroxide ion. It is a 1-to-1 relationship, which means the concentration of both of those things would be the same. Same thing with our calcium chloride. When the calcium chloride breaks apart, you get a calcium ion and 2 chloride ions. But in this case, we're interested in the calcium, which is also a 1-to-1 relationship. So that's again why we could use the entire concentration there for the whole thing for each of those individual ions. By the way, if I was doing something different and I wanted the concentration of the chloride, I would need to take the concentration and multiply it by 2. Yeah, so again, it does change if it's not a 1-to-1. All right, so now that we got the concentration of each of those ions in the solution, we're ready to put it into our Q expression. So we're going to take 9.98 times 10 to the minus 2. We're going to take our hydroxide, which is 3.99 times 10 to the minus 4, and forgetting not to square it there. So we'll square it. Giving us 3.99 to the minus 4 squared times 9.98 to the minus 2, right? No squarage. Going to give us we'll call it 1.6 times 10 to the minus 8. Any question on that calculation? All right, so again, it's important to make sure that you get the proper concentrations before you go into the Q expression here. You do want the concentrations of it, obviously, in the mixture when they come together. So at this point, what we want to do is take our Q value, take our KSP value, which was given to us in this case. If not, we would look it up, obviously, in a table if necessary to do so. And we want to compare them. So in this particular case, our Q value versus our KSP, our Q value is less than, greater than. It is less than, right? So our Q value is to the minus 8. Our KSP, I believe, is to the minus 6, even though I scribbled all over it, but I think it's to the minus 6 there. That means our KSP value is actually larger. Would I expect a precipitate to form in this case? The answer is no, precipitate. It would actually go the opposite way towards the product side, and you would have aqueous ions, basically. So although solubility rules tell us that this should be insoluble, we should expect a solid to form. A very big determination as to whether or not you actually see the solid is the concentration of the ions. In this case, although we did put them together properly, we do not have the right concentration, so we would not expect a solid to form in this case. Question? Was on the quiz? No, this is beyond the exam, though. Yeah. Did we not finish that one? I think we did, right? Yeah, I think we already went over it. Yeah. Other questions? All right. So again, this is 3 things that we just talked about here that can have an effect on the solubility of a solution. Again, the presence of a common ion will pretty much decrease the solubility. The pH adjustment could either increase the solubility or decrease it, depending on kind of if we're dealing with an acid or a base. And here, the concentration of ions are really important in terms of whether or not you will actually either see the solid form or not form. Again, even though solubility rules tell us it should form, because of those concentrations, they may not form. Also why in qualitative analysis experiments, although we don't do a lot of that part anymore. Every time you add a reagent, although we don't sort of measure out reagents when we're doing qualitative analysis, when you add reagents, you're basically just adding more water, so you're continuously diluting it. So if you're not really careful, you could create a situation where you drop the concentration of the ions too low in a qualitative analysis experiment, and you may not actually see the precipitate come out because of that. And that's also why there's a lot of steps where you will concentrate down your solution to get rid of the excess water to make it more concentrated. So those concentration of those ions come up, and you should see the solids that should form. Any questions on that there? Another really kind of important aspect of KSP is really in that vein of qualitative analysis sort of experiments. It is sometimes called selective precipitation. So much like in those experiments, you basically have solutions that have ions floating around. And the goal here is to sort of precipitate out certain ions, but kind of keep the other ions still floating around in the solution. So it's selectively going in there and precipitating those things out. So why would you want to do that? Why is it important to sort of understand how to do that properly? Well, if you were just going to go sort of visually and try to separate out stuff in a solution, if you happen to have a solution that had bromide ions floating around and chloride ions floating around, and you decided I'm going to precipitate those guys out by adding silver, and it will precipitate out those guys. You will make silver chloride, you will make silver bromide. That is those two pictures right there, which pretty much is a white solid on both cases. So if you sort of added the silver with not really understanding the proper way to do that to benefit keeping one of those guys in solution and keeping the other one out, there was really no way for you to go, I think this little white solid is the silver chloride, maybe this one is the bromide. You're not going to be able to really distinguish, either of those guys. So we could actually use KSP to our advantage to help us understand what we should do in terms of the silver concentration to only precipitate out one of those ions basically at a time. So in this question, it wants to know what is the concentration of silver that you would need to basically precipitate out just the silver bromide and basically leave the chloride ions still floating around in the solution if you had those ions in a concentration of 0.02 molar. So your goal is to add the silver, take out the bromide as a solid, and leave the chloride basically still floating around. So we know the two sort of KSP reactions that we're going to get. We have silver bromide, which we can look up the KSP value there of 7.7 times 10 to the minus 13. We also know the silver chloride would be the other one. So if we take the silver bromide, the KSP expression here would be our silver ion times our bromide ion, and that would equal 7.7 times 10 to the minus 13. We know that the bromide ion and the chloride ion is in solution at that concentration. So if we rearrange the KSP expression and actually solve for the silver concentration, it would be 7.7 times 10 to the minus 13 divided by the concentration of the bromide ion, which we actually have. So we can actually put that number in, 7.7 times 10 to the minus 13 divided by 0.02. And when we do that, we will end up with 0.02 7 minus 13 divided by 0.02. Gives us about 3.9 times 10 to the minus 11 molar. First off, any questions on that calculation there? So that calculation and that number represents something. What does that number represent in this case? That number is the concentration of silver. When I get the silver concentration to that number, what will start to happen? You will actually start to see precipitate form. So that number is the minimum concentration of silver that you would need to start to see a precipitate form. So what that tells me by using the KSP in this case is I got to get the concentration of silver to 3.9 times 10 to the minus 11. I then should start to see some white solid form. And I would be probably pretty confident that that white solid is silver bromide, but let's check to make sure. If we do a very similar calculation for the silver chloride here, and we use the KSP for our silver chloride, KSP is equal to the silver concentration times the chloride concentration, which is 1.6 times 10 to the minus 10. Again, solving for the silver concentration would give us 1.6 times 10 to the minus 10 divided by the chloride concentration. Putting in our number, 1.6 times 10 to the minus 10 divided by 0.02 will give us a concentration of 8.0 times 10 to the minus 9 molar. That is the minimum concentration of silver needed to precipitate out silver chloride. Is that number larger or smaller than the amount of silver needed for bromide? That number is larger, yes? So if I take the silver concentration and I get it to 3.9 times 10 to the minus 11, I should start to see some white solid come out. I can feel very confident that the white solid that I'm seeing is the silver bromide coming out. I could even keep increasing the silver concentration all the way up until before 8 times 10 to the minus 9. And if I still see solid come out at that point, as long as it's below 8 times 10 to the minus 9, I could safely feel that it is still silver bromide at that point. I could continue to add silver, keeping the concentration lower than 8 times 10 to the minus 9 until I do not see any more solid, right? At that point, I can feel really confident that I have just removed all of the bromide from that solution. At that point, I should take my silver concentration and take it up to 8 times 10 to the minus 9 or higher. I should once again start to see solid come out. And I can feel confident at that point that the solid I am seeing, which would also be a white solid, is silver chloride at that point, right? So by understanding the KSP, understanding the minimum concentrations, let's say our precipitating reagent in this case, which would be silver, we could actually selectively take out each of those ions as solids. Obviously, we could centrifuge it, right? Pour off the liquid, right? Keep the solid, do whatever we want to do with it, take it home with us, probably not. But we could do whatever we want to do with it here in this case. And we can selectively precipitate out each of those ions by understanding the KSP and really those concentrations. So really in this case, we would need to keep the silver concentration greater than 3.9 times 10 to the minus 11 to start to see the bromide come out, but less than 8.0 times 10 to the minus 9 molar to prevent any silver chloride from coming out. Question on that there. What would happen if I had both of those ions, both the bromide ion and the chloride ion in there, and I just grabbed the bottle of silver off the shelf that was basically, say, greater than 8 times 10 to the minus 9 and started dumping it in there? What would happen? Everybody would precipitate out at once, yeah? So you wouldn't, again, you'd be in that beginning situation of, I don't know which one's which, right? So again, if you started way too high with your silver concentration, you wouldn't be able to selectively precipitate those out. So understanding the KSP here allows us to figure out, how to really maintain or monitor the precipitating reagent to get the precipitation that we're looking for. One last thing here, just looking at the KSP values in this case, could I compare them to determine which one should precipitate out first? I can in this case. They both break apart into 2 ions. In this case, it is the silver chloride that has the larger KSP value, which means it should be more soluble, which is why the question asks to precipitate out the bromide first, because the bromide has the smaller KSP value, which means actually less soluble in this case. Question on KSP. All right, we'll lay it up there for today.